We all think we know what gravity is, right? An apple falls, the planets go around the sun. It's some kind of force that pulls things together. But what if that entire picture, the one we all learned in school, is just wrong? What if gravity isn't a force at all? So let's dive in and unravel this whole thing.
Okay, so let me ask you something. Right now, as you're sitting or standing there listening to this, are you accelerating? I mean, the obvious answer is no, of course not. You feel perfectly still. But what if I told you that according to Einstein, you are absolutely 100% accelerating?
And look, this isn't just some weird thought experiment. The physicist Sabine Hossenfelder says it perfectly. Since there's no actual force pulling you down, the only thing that explains what you're feeling is that you're accelerating upwards. In fact, if you put an accelerometer, the device in your phone that measures this stuff, on your desk, it won't read zero. It'll register a constant upward acceleration of 9.8 meters per second squared.
So, what is that feeling we call weight then? It's not a gravitational pull. It's the very real, physical force of the ground or your chair pushing up on you. It's stopping you from taking the path you're supposed to take through the universe. Your body is being constantly shoved upwards, and that resistance is what your brain interprets as weight. To figure out how we got to this wild conclusion, we actually have to go all the way back to 1907.
You know, this whole mind-bending revolution in physics really started with what Einstein himself called his happiest thought. He was trying to figure out how to make his theory of relativity work for acceleration, not just for constant speeds, and the answer just hit him in this incredible moment of insight.
And there it is. That's the key. Einstein realized that someone in freefall is weightless. An astronaut floating in space, a skydiver before they open their parachute. From their point of view, in that moment, gravity has just vanished. This was the light bulb moment that changed everything. What if freefall isn't really falling? What if it's the most natural, pure state of motion there is?
And this idea leads right into what's called the equivalence principle. It's a bit of a mouthful, but the idea is simple. It basically says that if you're in a small, closed-off area, you can't do any experiment to tell the difference between feeling gravity and just being accelerated. They are experimentally the same thing.
The classic sealed box experiment just nails this point home. Imagine you're in a box with no windows. If it's sitting on Earth, you feel the floor pressing against your feet, right? Now let's put that same box in deep space, far from everything, but it's being pushed by a rocket accelerating up at 9.8 meters per second squared. You know what? The floor would press against your feet with the exact same feeling. You would have no way of knowing which reality you were in.
Okay, so if gravity isn't a force, then what on earth is it? Well, the equivalence principle pushed Einstein to a conclusion so radical it changed physics forever. Gravity isn't something that happens in spacetime. Gravity is the shape of spacetime.
Well, in this new picture, you have to imagine that massive things like planets and stars literally bend and warp the fabric of space-time around them, kind of like a bowling ball on a trampoline. Everything else then just follows the straightest possible path it can through this curved landscape, and that path is called a geodesic. So an apple falling or the Earth orbiting the sun, they're not being pulled by a force, they're just following their natural straight-line path through a universe that's been curved.
Yeah, just let that sink in for a second. What we have called the force of gravity our entire lives is really just what it feels like to move through a warped geometric universe. Free fall isn't some special state, it's the most normal, unforced motion there is, just following the natural contours of space-time.
And the crazy part? The math backs this up like perfectly. When you calculate the total four-dimensional acceleration of an object that's just freely falling, you know what you get? Zero. A big, fat zero. By the very definition of general relativity, it is not accelerating. The only time you see acceleration in the equations is when a real physical force, like the electromagnetic force of the ground pushing on your feet, gets involved.
All right, so you might be thinking, okay, got it. Gravity is just space-time curvature. Case closed. But, well, it's a little more nuanced than that. There's actually a pretty subtle debate that comes from Einstein's own work about what we should even call the gravitational field. So here's the breakdown. On one hand, you have Einstein's original view, where he basically saw gravity as the whole phenomenon of freefall itself. Space-time curvature was the reason for it, but not the field itself. The more modern view, though, tends to define gravity as the curvature itself, the thing that you can actually measure through effects like stretching and squishing.
So what's the actual physical proof that space-time is really curved? Well, it's something called tidal forces. This is that stretching and squishing effect. Think about how the moon's gravity pulls on the oceans. It pulls harder on the side of Earth closer to it, and that difference is what creates the tides. That stretching is the direct evidence of curvature, and you can't make it disappear just by changing your perspective. It's real.
Okay, wow. We've covered a lot of ground here, from Einstein's happiest thought all the way to the geometry of the cosmos. So let's put all the pieces of the puzzle together and explain what is really happening to you right at this very moment.
So let's walk through what's happening to you right this second, step by step. First, the mass of Earth is bending the grid of space-time all around you. Second, your body naturally wants to follow the straightest, easiest path through that curved grid. That's the geodesic. But third, the ground gets in the way. It stops you. So fourth, the ground pushes back with a very real, physical upward force. And finally, fifth, you feel that constant upward push and acceleration, and you call it weight.
All right, so let's just nail down the big takeaways here, the things you absolutely need to remember from all this. First, gravity is not a force pulling you down. Second, free fall, being weightless, is the most natural state of motion. Third, just standing still on Earth means you are in a state of constant upward acceleration. And finally, that feeling of weight is just your body experiencing that acceleration.
And that, of course, leaves us with one last kind of mind-blowing question to chew on. If standing still is actually acceleration, and just falling is the most natural thing you can do, what does it even mean to be truly motionless? General relativity just flips our most basic understanding of the world on its head, all because gravity, as it turns out, is not a force.